Hello, everyone. Thank you for joining us today. I'm Ma Yifeng, the speaker for this topic. Here are my amazing partners. They are B2A Hicks, Green Bamboo, and Jia Haotian. It's my honor to introduce our research in network load balancing, aka NLB. First, this is my agenda. First, we will cover the NLB simply. This includes what it is, how it works, and the vulnerabilities we found in Windows NLB. Next, we will propose mitigation measures and provide some takeaways. So, what NLB is? As shown in this diagram, NLB is a technique used to distribute incoming network traffic across multiple servers. When a client sends a request, it first arrives the NLB virtual IP. This virtual IP is a single point for clients. From there, NLB decides how to distribute the request to one of the available hosts based on its load balancing algorithm. Each host has its own detected IP, which is used for management. And they all share the same virtual IP for handling client requests. The purpose of NLB is to enhance availability and scalability, ensuring that no single server is overwhelmed with too many requests, providing a seamless and efficient experience for end clients. So, how it works? Now, let's look at the components of NLB in more details. When we install the NLB feature in Windows, as you can see on the left side, it adds some files. We may interact with is NLB MGR. It used to configure and manage NLB clusters. On the right side, we have a breakdown of how NLB integrates within the system. At this layer, we have the server application, which receives traffic routed by NLB. At the kernel level, the NLB sys driver is here to core component to handle the NLB process. This driver works closely with the TCP IP stack, which intercepts incoming requests and then distributes to the network adapters. In fact, the NLB driver acts as the bridge between the network requests coming into the system and the network adapter, ensuring seamless load distribution across all hosts in the cluster. So, how it works in Windows NLB, the heartbeat feature and the convergence process ensure the reliability, the high availability of the cluster. Each host sends and receives heartbeat packets to check the online status of other hosts in the cluster. If a host fails to respond within the specific time frame, NLB treats it as inactive, triggering the convergence process. During the convergence, the active host redistribute the network load, keeping service continuous and load balancing. This process is important for NLB's fault tolerance and automatic recovery capabilities. And these core functions are mainly handled by the NLB sys file. Next, we will dive into the NLB code and walk through the process of handling heartbeat packets in NLB. NLB core receive packet is the entry point when a heartbeat packet arrives. It receives the packet and passes it for subsequent processing flow. The packet is then passed to NLB core receive heartbeat, which is responsible for validating that is a normal heartbeat message and call different processing function according to the type of heartbeat packet. If the heartbeat relates to membership, the NLB core receive membership heartbeat checks and updates the status of the loads, ensuring consistency across the cluster. For identity-related heartbeat packets, NLB core receive identity heartbeat will update identity cache and the NLB IP list. If there are any no other protocol data in the heartbeat packet, the NLB core receive NR protocol data function, passes it, and updates the status of the cluster at the same time. So this is the part about our cases introduced. We will introduce how we found the vulnerabilities based on NLB structure. Next, we will show 5 cases. And the case 1 is about out-of-bounds read and write by evil host ID. In NLB configuration, the host ID servers are the unique identifier for each host in the cluster. It's typically assigned a value between 0 to 31. As the NLB clusters support up to 32 hosts, identity heartbeat is a specific type of heartbeat packet used in Windows NLB to ensure that each server in the NLB clusters has a unique identity. When a new host is added to the NLB cluster or when an existing host restarts, the system will send an identity heartbeat packet. The packets are processed by the function NLB core receive identity heartbeat, and the code like this. There are 2 functions, NLB core receive identity FQDN payload and NLB core receive identity DIP payload, which will reference the host ID set here to index the identity cache. Next, let's take a look at the identity cache structure used in NLB. As shown in this diagram, the identity cache is an array of 32 entries. Each have a specific host ID. The host ID is an index for identifying each host in the cluster. Range from 1 to 32. The DIP entry list has a linked list where each DIP entry stores detailed IP information of the host. So let's guess what happens if the host ID goes beyond this range 1 to 32. Let's make a special heartbeat bucket and set its host ID to a value bigger than 32. Next, let's check the 2 core processing functions of the identity heartbeat packet, NLB receive identity FQDN payload and NLB core receive identity DIP payload. We can see function NLB core receive identity FQDN payload is to receive FQDN payload and update it to the global identity cache. As shown in the code, an attacker can make the host ID to an arbitrary value, which is then used directly in the NLB sys without validation. In this case, we attempt to construct an NLB heartbeat packet with a host ID hex 22222, which is more bigger than 32. This index can fall outside the array's intended bounds, resulting in an out-of-bounds write. This out-of-bounds write allows the attacker to overwrite nearby memory locations with the controllable data, as shown in the memory move operation at this. So we can achieve the crash in Windows Receive Identity FQDM payload. Now, let's take a look at the NLB core identity cache at the DIP entry function. This function plays a key role in keeping the identity cache. It constructs a DIP entry based on the provided DIP address, and it inserts it into the DIP entry list related with the host ID. However, this operation makes a potential problem similar to our previously discussed NLB core identity cache at DIP entry index the identity cache array using host ID. So we modified the POC to enter the function and set the host ID to hex 11111. In this case, when the function attempts to access the IP entry list, it could lead to an out-of-bounds read and write. So, the NLB core identity cache get DIP entry function also falls victim to a similar vulnerability due to how it references host ID. It's designed to get a DIP entry from the identity cache based on a given host ID. The function looks up the IP entry list to find the corresponding entry. However, in the above some vulnerability triggering path, we found that there are possible ways to RCE here. For example, in the NLB core receive identity FQDM payload function, we can control each parameter of the memory move function. Maybe we can find a module outside of KCFG and modify the function pointer to control the RIP register like this. We also found something interesting when study the old WLBS code with the refactored NLB version. In WLBS, there was a safety check to make sure the host ID not go over 32, but in the new NLB module, that check is missing. This shows how refactor code can sometimes accidentally leave out important checks, which could create vulnerabilities. Our case 2 is about integer overflow in TLV header. In this example, we are looking into a vulnerability within the function NLB core receive DIP payload, which was previously introduced. The issue arises during the length calculation from the TLV header. Specifically, the length is computed by this formula here. The problem here is the undesigned integer calculation. When the value of length is less than 2, will triggers an integer overflow and bypass the subsequent safety check, which is this one, and OOB rates when the code tries to access A4 with the statement. But these bugs of this kind are not easy to trigger crashes. So let's observe it from one debug. This diagram is the view of one debug. NLB filter receive net buffer list is used to receive NLB related packets, with its second parameter being the buffer list of the received packet. The net buffer list can be viewed as a linked list, where each node represents a buffer for a network packet. Each node contains a pointer to the buffer of the data packet, as well as other information related to the packet. So observe the first net buffer point to hex to this value, and the buffer of the packet is described by MDL. We observe current MDL. The structure information is as follows, where byte count is hex 54, map the system VA is this one, and the safety range of the buffer is this value at hex 54 to this value. Let's follow this value, then triggered the integer overflow and successfully bypass the net check. We can access 16 bytes out of bounds from the buffer and address. Our case 3 is about risk condition to use after free in NLB IP list management. In our case study 1, we discussed how the NLB core receiver identity DIP payload function updates the DIP entry list under the NLP IP list, which is a list of all detected IPs across all hosts in the clusters. Now, let's move on a trace condition vulnerability we discovered in the management of the NLB IP list. When analyzing how the NLB module accesses shared resource, we find a critical issue that the NLB list check item function, which is called by NLB core IO control query filter, does not perform any locking operation on the shared resource. As shown in the diagram, the code gets a shared resource address and accesses the items array, but without a lock. Now we just need to find a release point, like NLB IP list IP increased size. Whenever a new identity DIP payload is received, the IP address information is added to the NLB IP list. This causes the NLB IP list to dynamically expand, and the items array and the hash table to handle more IP address. This operation makes the original items and the hash table get raised. As shown in the flow, if NLB IP list increase size is triggering where the items array is still being accessed by NLB IP check item index, the original memory blocks from items array and they are released. The subsequent access to the released memory triggering or use after crash finally, where concurrent operations on shared resource like the NLB IP list can result in a risk condition vulnerabilities. Our case 4 is about risk condition 2. And the risk condition can also lead to DOS. NR protocol is an internal protocol within the NLB system, used for communication between nodes in a cluster to ensure that all nodes maintain a consistent view of the cluster's membership and load information. NLB core load processing heartbeat internally passes membership heartbeat, include send NR protocol and triggers convergence when a change in the cluster is detected. When executing the above function, it will read the NR protocol pointer RCX as hex C9B8 and passes it to NLB core NR protocol start sending as the first parameter. There is a multiple thread security problem. The NLB core load processing heartbeat function does not acquire the knock when accessing this, which will cause problems in some cases. If thread 1 is executing this code, thread 2 is executing this function at the same time. This will release the value of the offset hex C9B8 pointer and make it to 0. Next, let's analyze the crash in this case. At this point, the pointer at offset hex C9B8 has already been set to 0, and when the function NLB core load processing heartbeat is called, it invokes NLB core NR protocol start sending. Inside this function, it will try to get a keyspring lock pointer. However, since the pointer at hex C9B8 is 0, the attempt to access it needs to a 0 address dereference as shown in the crash trace and finally cause a DOS. Now, we will introduce this bug, or case 5, moderate severity, but unauthorized DOS, with being defined as moderate severity DOS, but we still think it worth to be mentioned. An attacker can repeatedly send special packets to trigger a memory leak bug in the remote NLB server, thereby exhausting the target's non-paged memory pool. As this memory is never released, eventually this will cause a BSOD of the current NLB host. This course stack showcases how NLB handles receive data by dynamically expanding the victory container to store IP address from the packet. During its execution, it checks whether the vector has enough space for the new element or not. If not, it calls NLB vector reserve to add more space. The logic of NLB vector reserve using NDS allocated memory with tag to allocate non-paged memory. However, through our analysis, we found a big problem. The non-paged memory isn't released in the code. Every time NLB vector reserve is called, it increases the all allocated memory size dynamically, with each expansion increasing by at least 1/3 of the current size, because non-paged memory is very little in kernel space. This repeat growth quickly uses it up. So let's make a special NR packet and send them to the NLB host. This makes the host enter the NLB vector reserve process, which keeps allocating non-paged memory. By analysis, the NLB driver will get the structure of the NR packet and make the payload to trigger this. To remotely trigger the allocation of non-paged memory, our NR packet must be bypassed the check within the NLB vector reserve call stack. As shown in the diagram, the NR packet structure includes like magic, function ID, type, and index. Each one is crucial for deciding how the packet is handling. The first one is about the magic. The magic field must match specific values, such as hex code 01C0 or hex code 01F0 to send the packet to the right handling function, like the NLB core receive membership heartbeat or NLB receive NR protocol data. Number 2 is about the function ID. Inside the NLB core NR protocol receive data, the function ID field undergoes a switch case check. If function ID is true, it directs the code flow to the NLB vector reserve. And number 3 is about the type. We need to bypass check of NLB core exception list IPv4 which means that we need to set the type field to true. And the next one is about the index. The index field is checked to ensure it must be less than or equal to hex 20 to bypass the safeguard conditions. As we completed the previously analysis, we finally construct the NR packet as shown like this. After our POC keeps sending a special request, we can see through when debug that the NDS allocated memory with tag has failed to call, which means that the non-paged memory pool in the system has been exhausted. So, if an attacker can continue trigger an LB vector reserve with specific network requests, they can cause the non-paged memory to be exhausted, make a memory leak. Once the non-paged memory is exhausted, the system and the applications will cause many exceptions and causing crash like this. Now it's our concluding part. This is a summary of the main points covered earlier. The number 1 is exploit arbitrary host ID manipulation to trigger out-of-bounds read and write, enabling unauthorized arbitrary code execution. Number 2, carefully crafted TLV headers can cause integer overflow, which can lead to out-of-bounds read. Number 3, a risk condition that triggers use after free in NLB IP list, potentially allowing arbitrary code execution. Number 4, exploiting a risk condition in NR protocol to induce a denial of service, compromising NLB service stability. Number 5, though of moderate severity. This vulnerability can be exploited remotely without authentication, compromising NLB service stability. In fact, we reported 9 NLB service-related vulnerabilities to Microsoft Security Research Center, which eventually merged into 2 CVEs. And these are some mitigation strategies. Number 1, permit fixes are highly recommended. Number 2, some moderate severity vulnerabilities may take longer to fix. Before that, it's recommended to pay attention to abnormal NLB heartbeat protocol packets. Number 3, add a firewall policy to block hosts other than NLB host from sending heartbeat protocol to NLB host. Here are some takeaways. It's crucial for security teams, especially those in organizations utilizing the NLB service, to pay special attention to NLB heartbeat traffic. Heartbeats are fundamental for maintaining the cluster synchronization and health monitoring. However, as we've demonstrated, these packets can also be manipulated to exploit vulnerabilities, potentially leading to serious security issues. Regularly inspecting and analyzing this type of traffic could help detect unusual patterns or signs of exploitation early on, reducing the risk of attacks targeting NLP compliance. We also should focus risks in code refactoring. This is an inherent risk when refactoring legacy code. In many cases, security checks implemented in older versions might be inadvertently omitted or altered during updates by developers. This can introduce new vulnerabilities even in areas that were previously secure. Therefore, rigorous security audits and thorough testing should be a part of the development process, especially when dealing with critical complaints like NLP, to ensure that previously fixed issues do not resurface. Where some vendors may classify certain vulnerabilities as medium severity, and leading to longer patch timelines or even a lack of resolution. These issues shouldn't to be underestimated. Even medium-rated vulnerabilities can impact the stability and the security of the server environment if exploited under specific conditions. It's important to understand that these risks might not always seem urgent, but can have severe consequences if left unaddressed, especially in production environments where system uptime and reliability are paramount. So there are some opportunities for bug bounty hunters. Refactored modules can be vulnerable targets for bug bounty hunters. They might reproduce old bugs or reveal new attack surfaces. Moreover, the abundance of technical articles and related source codes often make it easier for security researchers to analyze and identify potential vulnerability in these areas. Our topic is over. Thank you all for your attention and your time. I'm happy to take any question you might have. You can contact us in Twitter. Thank you all.